Hello, in this video I'm going to talk about the power of energy that goes into a circuit element. So here is the situation. I have some kind of a device in here. I don't know what it is, I don't care. This might be a resistor or a battery or a capacitor, or it might be very complicated. We usually call these kind of things whose structure we don't know as black box devices. So these are black box. Black because I don't know what is inside. I only know the current that goes into it and the potential drop on it. And for this, of course, we have this convention. We choose an arrow in here. This is our choice. We choose it in any way we want. And along that direction, we measure the current. So there's a current. We also measure the potential drop across the device along that direction. So these are the things that we know. And just remember that these are signed quantities, so therefore they can be positive or negative depending on which direction you have chosen. In that case, if P is the power of energy that goes into the device, then this power can be expressed in terms of the current and the potential drop like this, as the product of these two quantities. So you can see that in here the direction of the arrow also does not matter, because when you change the direction of the arrow, both the current and the potential drop changes sign. So as a result, this power quantity is a quantity that doesn't depend on your choice of this direction. Okay, so here I'm going to discuss and prove that relationship, but let's remember what we mean by that power. So there's a physical device in here. So this device has some energy, and power is basically the rate of change of that energy. So there is some kind of an energy transfer to that device, and we are computing the rate of change of that energy. So how do we derive this relationship? So for this purpose, I'm going to look at this part of the circuit. So this is the same circuit again, but let's remember the conventions. So I'm going to choose this point as, call that point as A. Right, this is A, this point as B. The potential drop that we define is the negative of the change. So the change would be VB minus VA if I move along the arrow. But here, this is VA minus VB. It is the opposite of the change. So that's the potential drop. It's the negative of the change when you move around along the direction of the arrow. So let's say that there's consider some kind of a time interval, and over that time interval, let's say delta t, the amount of the charge that passes over the device is called Q. So Q is equal to current times delta T. Okay, so Q is the charge of carriers that cross the device during that time interval. Okay, so as a result, the charge carrier has some potential energy. So let me write it down like this. This is the potential energy of the charge carriers. This can be written as charge multiplied with the change in the potential of the charge carriers. So since we know the potentials, this is basically the final potential minus the initial potential. So that's VB minus VA. Okay. And we have said that the potential drop is just the negative of that. So therefore, this is the minus V. So therefore, this is equal to minus Q times V. Okay, that means I'm not concerned about the sign of this thing, but the formula is correct. So it may happen that this is positive or this negative. So I'm going to discuss all the other cases at the end. So therefore, the the change in the potential energy of the carriers is given by this formula. How about the kinetic energy? Change in the kinetic energy of the carriers. Okay, in that case, I'm going to assume this. Let's say that this is a copper wire. Let me use this highlighter pen. This is a copper wire, and there's a copper wire in here. So the copper wires are connected to the device. So in this wire, the properties or the statistical properties of the charge carriers are exactly the same as the properties of the charge carriers at that copper wire. So as a result, I mean, the charge carriers are moving inside the copper, and they have some certain velocities, typical velocities. So therefore, if that's the case, then I would expect that the kinetic energy of the charge carriers do not change. So therefore, the change in the kinetic energy of the carriers is equal to 0. So that means this change in the potential energy is the change in the mechanical energy of the charge carriers. So therefore, we have delta E carrier total energy, the change in the total energy of the carriers is given by minus Q times V. Okay, but this change, I mean, during that motion, the charge carriers have also interacted with the device. So therefore, because of the conservation of energy, the energy of the device should also change, and that would be the opposite of the change in the energy of the carriers, because there's an energy exchange between the device and the carriers in here. So therefore, the change in the energy of the device is Q times V. So if I write it in terms of the current, this is IV times delta T. So therefore, let me just write it in terms of the delta. So delta E device divided by delta T, therefore is equal to I times V. Okay, and that's what we have called as the power. Okay, that's the proof of that relationship. So somehow the charge carriers are transferring energy from some parts of the circuit. So there are some parts of the circuit in here that I haven't drawn. So that's also another black box. So the charge carriers are essentially transferring energy from that part to the part where the device is. And the amount of the energy that is transferred to a device is given by that formula. So let's consider the special cases. So that's the special case when there is a resistor. So the black box is just a resistor. In that case, no matter in which direction I choose this arrow, the potential drop is and the current are at the have the same sign. So that means V and I have the same sign. So that means the power that goes into a resistor, which is given as V times I, is R times I squared, or you can write it in terms of V potential drop only, V squared divided by R. This is always positive. So that means the rate of the change of the energy of the resistor is always positive. So the energy of the resistor always increases. So that's the case where the energy is converted into heat. So that's actually a nice example of a process that we call as dissipation. Energy is converted into essentially heat. And this process is always a one-way process. So this is the mechanical energy is converted into heat. So according to the second law of thermodynamics, you can never do it in the backward direction. There's only a forward direction here. So as a result, on a resistor, the power is always positive. There's energy, a positive energy always goes into a resistor. How about a battery in here? So I'm going to show it with this symbol, but I'm going to talk about the EMF devices later on. So let me just call this as battery. So in that case, let's again choose the, I'm just going to choose the polarity of the device like that. So if these are points A and B, we know that VB is bigger than VA. It's actually equal to VA plus the EMF of the device. In any case, if I draw the arrow like that, so in that case, I is positive, V is negative, which means the power that goes into the circuit element is negative. Okay, that's one example. All right, I have to add a warning in here. So that thing actually depends on what else is there in that circuit. So let's just say that there's just a simple resistor in here, in which case the current is really along that direction, it's positive along that direction. And so therefore, we have that situation in here. So the power that goes into the battery is negative, which means negative energy goes into the battery, which also means that the battery provides energy to the rest of the circuit. Okay, so the rate of change of the energy of the battery in that case is negative. Okay, which means battery is providing energy to the circuit. Okay, we can continue like that. There are other examples of devices. For example, there are these electric motors. It's not you cannot treat this as a resistor. So as a result, the current voltage relationship for the case of an electric motor is actually complicated. It also depends on whether this motor is doing some work on something, or is it just, I don't know, rotating freely. In that case too, the potential drop here changes. But what you can say in here is that as long as the electric motor is working in here, the current and the potential drop should have the same sign, because we know that this is consuming energy. And so in that case, the rate of change of the energy of the motor is always positive, which means the current and the potential drop should also have the same sign. So therefore, their product should also be positive. Okay. After that, we are going to discuss what these EMF devices are.